Okay, let's take a look at R being the set of all ordered pairs x comma y, satisfying the properties x is between -2 and 2, and y is between -3 and 3. Then let's look at two parts here. For part A, we are going to estimate the integral of the function root 9 minus y squared, and then we will find the value of the integral exactly. So first, as an estimate, here's the input space, right? So x from -2 to 2, y from -3 to 3. The input space we've called capital R is shown here in yellow. And then it's an estimate. So we're just going to split up the x interval into three equal-sized pieces here. So going this way, I just drew, okay, so the outer lines don't count, but drew two inner lines. So then there's this one yellow strip between blue vertical and blue vertical, and then another yellow strip between blue vertical and blue vertical, and a third vertical strip between blue vertical and blue vertical. We'll subdivide the y interval into four intervals. So just because I felt like using different values for m and n, so we've split into four pieces this way. So there's four horizontal strips. So delta x, it's 2 minus -2 all over 3, 4/3, and then delta y, so you see a depiction of it right over here. That is 3 minus -3 all over 4, so that's going to be 6 over 4, in other words, 3 over 2. And then in each of these individual subintervals, so there are 12 like smaller regions here, right? Pick a sample point, and they don't have to be uniformly picked. So you can see my dots that I've chosen are kind of all over the place. But in each one of these places, I'm just, and then all we do is, well, we're supposed to remember. So there's a volume. So delta x and delta y are always multiplied together by a z value. So I just factored that out, the delta x and the delta y. What are the z values that we need to add up then? So how about over here? This would be, so this function root 9 minus y squared. That would be like right here, right? This is root 9 minus -2 squared, and then here this is root 9 minus -2 squared, and here is root 9 minus -2 squared, and so on, right? So we will just keep doing this for all of every single point here corresponds to a certain z value, and assuming there's no typos, these, sorry, let's try this again. Root 9 minus y squared, oopsies. Okay, so let's see, so -2 is right here, huh? On the y-axis. Okay, so that's why you see root 9 minus -2 squared written 3 times. It's for this dot, and that's that dot. Then you see root 9 minus -1 squared for this dot, and this dot. Then you see root 9 minus +1 squared for this dot, and that dot. So 1, 2, 3 of those. And then root 9 minus 2 squared, root 9 minus 2 squared, and then the z value here is root 9 minus 3 squared. It's just because we picked the dot in a slightly funky location. This happens to be 56.3-ish in a calculator. So yeah, just to go through and step through, this z value came from that point, this z value came from that point, and so on and so forth. So we'll just do a little colorization like that. And then that last one, I know it's funky. We just happened to pick a point that wasn't right in the middle of that little mini rectangle. It was just kind of right on the edge. Why not? Okay, for the 12th subrectangle, we chose the point 1, 3 and had f of 1, 3 actually was equal to 0 as part of the sum. That didn't really add anything to the sum, did it? Doing this was admittedly not uniform, because for the 10th and 11th subrectangles, the y-coordinate was 2 instead of 3. But we just did this to illustrate that we're allowed to do that. We can make that choice. It leads to a slightly different number, but it was an approximation anyway. Geometrically, we're just really adding the volumes of 12 rectangular prisms, right? So each rectangular prism had one of its dimensions was delta x, one of its dimensions was delta y, and the other dimension was given by a z value by plugging in a choice of x and y into the function f to get the value of z. We just happen to factor out delta x and delta y in the beginning. Okay, so we found this estimate of 56.3018 as the volume. Now let's find the exact value, which was the other part of the question. So let's try describing what z equals root 9 minus y squared looks like without using any technology first. What's a hint here? Notice there's no x in this at all. So if we just were to look at the equation z is equal to root 9 minus y squared, what would just graphing that on the yz plane look like? Well, this should be the upper half of a circle of radius 3. Think about it. Take this equation here, square both sides. Z squared is equal to 9 minus y squared. Add y squared to both sides. You have y squared plus z squared equals 9. So that's a circle of radius 3, but because of how this is set up with just a plus root, we're just talking about the upper half circle. Now this propagates in the x-axis direction. So let's say this. This is shaped sort of like an airplane hangar, if that makes sense. By the way, if we just see the same shape, it's a half circle. The half circle has radius, 1/2 times pi r squared. So pi times 3 squared, but then half of that, right? So that, but we have that half circle area, but we have many, many copies of this because it propagates in the x direction. X, remember, ranged from -2 to +2. So for an entire length or width of 4, we have that. So the exact volume should be 4 times the area of the half circle, times 1/2 times pi times 3 squared. So in a calculator, 18 pi is going to be 56.5487, which is actually fairly close to our earlier estimate of 56.3018. Okay, so the volume of these 12 rectangular prisms that we computed, the sum of the 12 volumes, kind of resemble the actual airplane hangar shape and has nearly the same volume.